Okay, we're talking chapter 19, maybe. I don't know. Last time we talked a lot about complex ions and coordination compounds and how to go about sort of naming these guys. So a reminder that we can have either a positive complex ion and a negative counter ion, which in that case, we do use just the regular name of the metal, and we do use Roman numerals there, and do our ligands ahead of it in alphabetical order. And really, our counter ion is really just the name of the counter ion in most cases. If it's a polyatomic ion, if it's really just an anion, it will still end in the IDE at the end of it, is like chloride or something like that. If it's sort of switched around, we have our counter ion that is positive, and our complex ion that's negative. We still sort of do the same thing, pretty much going to just use really just the name of your counter ion in that case, regardless of how many there are. Your complex ion will end in sort of that older version of the name, like ferrate or plumate or something like that. Also, we'll still have some Roman numeralage happening there. And again, we will still have our ligands in alphabetical order kind of before it. We talked about some isomers as well with coordination compounds, and there's different types. We also talked about chiral compounds, which have a mirror image that does not superimpose. So that was our hands. That you take the mirror image out and you can rotate it around and it will not superimpose on each other. We finished up talking about crystal field splitting, which is when transition metals, for example, have ligands attached to them. There's sort of a separation that occurs of those d orbitals where they house their electrons, and that is what is known as the crystal field splitting, sometimes just kind of abbreviated with the little delta symbol. And there's going to be this energy difference of these sort of 5 orbitals. In the case of octahedral, which I think is what we've been looking at here, we get kind of like 3 of the d orbitals on the bottom, 2 on the top. And it does affect, as we talked about, how electrons will populate these orbitals. Again, if they kind of go in one at a time and see that the splitting is not that tremendously large, they will continue to sort of populate as normal one at a time and then come back and sort of fill everybody up. If we get a splitting where it's much greater in energy, what's going to happen is they're going to go this way and go, that's a little too big of a jump there. So they're going to fill the lower ones first before they sort of proceed to the higher there. And we could calculate this energy of the splitting. The crystal field splitting is really the same sort of energy equation you probably saw in Chem 50, which is our energy is equal to H times frequency, H being our Planck's constant. And obviously, that's our frequency, which is usually in reciprocal seconds is the units. We also could tie that into, if we know just the wavelength, for example, our c, which is the speed of light, equals our wavelength times our frequency. That means our frequency would be c divided by the wavelength, which can get substituted into here. And that would give us E is equal to hc over the wavelength. So either knowing the wavelength or knowing the frequency of a photon of light to sort of energize those electrons from lower energy d orbitals to higher energy d orbitals, you can figure out the sort of energy split that occurs there. Any questions up there? All right, so this is what we were looking at. So how do we know if we're going to sort of get a sort of big split there or a smaller sort of separation of those d orbitals? There's a spectrochemical series which helps us sort of make that decision. So on this side over here, these are considered weak field ligands, which means that the separation between the lower d orbitals and those higher d orbitals is going to be relatively small. And that means that when electrons do populate here, and this would be the electrons, by the way, from the transition metal, They would, again, just kind of go in one at a time like they normally would fill orbitals in the subshell and then come back and start pairing. Now, if you find yourself more on this end of the spectrum here, these are what are considered strong filled, which we have a little larger of a separation between those lower and higher d orbitals. And in this case, they're going to decide once they get to the end here, we rather fill bottom first before we kind of go upwards in terms of energy. This is going to give you two different types of compounds, is how they're sort of referred to. This over here on the left will give you what is sometimes referred to as a high spin complex. And it's high spin because there's a lot of unpaired electrons basically in that sort of arrangement. Over here on the right-hand side, we have more paired electrons, and that's going to give you more of what's referred to as a low spin complex. Sometimes people will use those words in problems, stuff like that, like, hey, draw it for the low spin or high spin. So they sort of do that. You could probably assume safely that it's the high spin sort of complex. You got a much smaller separation of those d orbitals, and they're going to kind of go in like normal one at a time. If you're doing a low spin, then you're going to have a lot more paired up electrons that are going to happen. Now, sometimes these guys in the middle, it's sort of a crapshoot there. So they'll sometimes will give you that information of, do it as it was a high spin or low spin or weak field, strong field. So they'll, a lot of times for guys in the middle, they'll kind of give you some information. If you don't get some information, sometimes it doesn't really matter. You could do low spin, high spin, or strong field, weak field. It will come out the same, depending on how many electrons you're distributing. So sometimes it really doesn't make a difference if it's sort of strong field or weak field, because frankly, you got like 3 electrons. So they're just going to fill the bottom no matter what you got going on there, if it's high spin or low spin, or strong field or weak field in that case. Any questions about there? So let's take a look at these here and a couple of these here just to sort of see what we want to do. So for example, if we look at this first one here, which is our NiBr6. First off here, the coordination number is going to be 6 in this case, right? As Br is monodentate. That also tells us we're going to be looking at the octahedral splitting. And that splitting is what we've been looking at, obviously, here with our non-squared orbitals on the top there, on the bottom, and our squared orbitals on the top. So we're going to get that splitting that's going to happen here. And what we want to really figure out first off, though, is sort of what is the oxidation state here on our transition metal. So if we go through that, our Br is -1, and there's 6 of them, gives us like a -6. Overall here, we do have a -2 charge, which means the nickel here is carrying a +4 oxidation state or charge in this particular case. And if we look at the periodic table there, nickel is 28, right? So nickel is 28 with no charge, which means if we did the electron configuration, that's a little argon 4s2 3d8. With nickel, with our +4 charge in this particular case, it means it has lost 4 electrons, so it has 24 electrons. As we talked about earlier, right, when transition metals lose electrons, they're going to toss out the S's first, yeah. So we're going to toss those out first, and that is 2 of the 4 we need. We also then need to delve into our D there to collect the other 2 out of there. So that's going to leave us an argon 3d6. So it is these 6 electrons here for nickel that's really what we're going to kind of populate into those orbitals that are being split here based on the ligands that are attached. Any questions on that so far? So how are we going to distribute them? We're going to go to our little series here, and we see that Br- is close to a weak field ligand, which means that the splitting here between our orbitals here is going to be relatively small. So when we go to populate the orbitals with our electrons and draw a little diagram, we would expect them to go in 1, 2, 3. And again, because this is a small split, is going to just kind of continue to feel like normal here. And at this point, it will come back and pair up here. And we can see a couple things here. We have 4 unpaired electrons, right? And that's a very common question when you're doing these type of problems, is like, how many unpaired electrons would you expect to have in this complex? Also, because obviously there's more unpaired electrons here, this is considered a high spin complex, as a lot more unpaired electron versus paired up electrons. So that would be the crystal field splitting diagram there. And we again have 4 unpaired electrons, and they would be high spin. Any questions on those there? All right, so why don't you do the rest of these here and see which come up. Draw the crystal field splitting, how many unpaired electrons we got going on for each of those. Yeah. So it's based on the ligand that's attached here. So the ligand here is Br, bromine, and bromine is considered on this scale here a weak field, which means it will give you a small sort of separation. Yeah. Other questions? Okay, give those a go, see what you got. You could consider F, you can consider a weak field if you like. Bless you. See, we'll start here with the other nickel guy, and our En, as was mentioned, is no charge, which means this nickel here is also carrying a +4, which conveniently enough means we will end up with the same electron configuration as we got going on down there. We do want to look at the ligand here, and the ligand here is En, which again is closer to the strong field, which means we're going to get a larger separation of those d orbitals. For dramatic drawing purposes, I'll draw them way up here. How's that? So we're going to get a pretty large split here. That means as we distribute these 6 electrons here, it's going to go here, here, here. Again, decide that's a little too far to jump up right at this moment. So it will come back here in this case, and we'll pair up them all. And we'll actually end up with 0 unpaired electrons, right? And this definitely would be a low spin complex, as they are pretty much all paired up in this particular case. By the way, the coordination number here is still 6, right? As that is bidentate the N. So that means you get a 2-for-1 deal on that, right? And that means it's still going to do the octahedral splitting, which is what we see here in this diagram. And again, we could obviously label them if we wanted to get all fancy, which, like, we're chemistry people here. There we go. Any questions on that one there? All right, so rolling over to iron here. Iron, just with no charge, is 26, which means that's an argon 4s2 3d6 happening. So looking here at the fluorine, which is -1, there's 6 of them. That gives us a -6. Overall, -3, which means the iron here is carrying a +3 charge. And that means that it will drop to 23 electrons. Going to lose our S's like we talked about before, and we will then also lose out a electron here in our D. That's going to give us a argon 3d5. So it is those 5 electrons that we're going to distribute in this case. And we'll take a look at it here. Get rid of this here, draw it over here. All right, so looking at our ligand here, which is F minus, and we can see it's, sort of in the middle. So I think I said we'll do it as a weak field in this case. So if we did it as a weak field, we again would have a small separation here, and distributing our 5 electrons, 1, 2, 3, 4, and 5 in this case, would give us 5 unpaired electrons, and definitely would be a high spin situation. Obviously, if we had it as a large separation, they would all pair up, right? Pretty much, except for one, and it would be more of a low spin. Looking at our next one here, Obviously here coordination number is still 6, and also here the coordination number is 6. So these are all, again, the octahedral splitting. -1 for our CN gives us a -6, -3 overall. So still carrying that +3. Difference here, the ligand attached is definitely more of a strong field ligand. So we're going to get that bigger separation of those d orbitals. And that means that we will have R3, and we'll go this way. Large. So distributing the 5 in this case will actually come back here and pair up, leaving us only one unpaired electron. And definitely would be a low spin complex. Question on how to draw those, figure out electrons, or anything like that. Yeah. And again, those are, like I said, very common questions are asked in these type of problems, like how many unpaired electrons would you expect, and is it high spin, low spin type of situation. All right, those are the ones we did. So here's the ones we just did there, and again, you can see more paired electrons giving us that low spin, and our high spin more unpaired electrons. Here's the orbital diagrams for high spin and low spin octahedral complexes, and again, on the left-hand side, way more unpaired electrons, which again is giving us our high spin. Larger separation, those d orbitals is going to force those electrons to pair up earlier and create more of a low spin. So what we've been looking at here, as I mentioned, is for octahedral complexes, which typically have coordination numbers of 6. Again, that's sort of that larger positive charge usually on that transition metal is where we find those coordination numbers of 6. Remember, it could also have tetrahedral complexes, and these are typically guys that have coordination numbers of 4. And it's a similar sort of split, except it's upside down than the last one here. So for tetrahedral, we actually get those 3 orbitals that were lower for octahedral actually being higher in energy than our 2 that we had on the previous one that was higher. So as electrons would go in here, it works really the same way. We would fill in. And then if it's too large of a split, we would fill down here first before coming up. And then obviously, if it wasn't a large split, we would fill them one at a time, and then obviously go back and pair them up. So this arrangement here is pretty much like the ones we just did there for octahedral, except it's just flipped around. We also solved for coordination number 4, square planar, which has a lot of variance happening there with our different orbitals. But again, kind of works the same way. You would fill it based on the levels of splitting that's happening here. So for us, you will be responsible for the octahedral splitting and the tetrahedral splitting, since they're kind of similar to each other, just opposite of each other. We'll leave the scary looking square planar alone here in this situation. Any questions on crystal field splitting, transition metals, complex ions? Chapter 19 wrapped up. Let's go to 21 here with nuclear chemistry, which is not organic. So nuclear chemistry here, we're going to see what glows in the dark and all that good stuff. So radioactivity, radioactive nuclei, which are pretty much your bottom rows there on the periodic table. They will decompose into smaller nuclei through radioactive decay. They're said to be unstable. It could happen sort of spontaneously. They will just continue to sort of decay until they hit something that's a little bit more stable. As we'll talk about as well, you could also sort of help it along by shooting a particle at something, and then it's going to become very unhappy and start to perhaps go through radioactive decay as that happens. When we do go through radioactive decay, or a nuclide, which is sometimes what they're referred to, it emits a lot of times particles as it's going through this process. That usually also involves a lot of energy that's usually given off in nuclear sort of processes. The parent nuclide is really the nucleus that's undergoing radioactive decay. We refer to what sort of develops afterwards is the daughter nuclide. As I mentioned before, pretty much anything above 84 there on the periodic table is going to be pretty much radioactive and will go experience through it. You've got things like uranium and plutonium and all those fun stuff, I suppose. Yes. So there's different types of radioactive decay particles and symbols that we see a lot in nuclear chemistry. So we remember our friend Rutherford who did. He did the gold foil experiment. I'm impressed. That's very good. We're gonna put that on the final. No. He used which one of these rays? So he did shoot alpha particles, right? Perhaps some of them scattered at large angles. A lot of them went through, perhaps. I'm not a Chem 50 throwback right now. So alpha particles, which surprisingly enough uses the alpha symbol. They are positively charged radioactive particles. They also use the alpha symbol, and they're really helium nucleuses. So in nuclear chemistry, they oftentimes will also use the helium sort of symbol for them. By the way, writing it like this, top number is? It is the mass number. The bottom number there is? Protons. It is also known as the atomic number, right? Which is the number of protons. While we're at it, the mass number is the number of protons and neutrons. There it is. We don't have to take a field trip to Chem 50. That's good. All right. So beta rays or beta particles, they use the beta symbol there. They're basically electrons. So you'll see the beta symbol used for it. You also sometimes see electron or the little E used for the symbol of it. And gamma rays are pure energy. You found those at the end of the electromagnetic spectrum, right? To the left of X-rays, when you looked at those things. And remember that where you have the visible visible colors. I'll spit it out. I don't know. The visible colors where you see colors, red, orange, yellow, green, and all the way to the end, right, was this high energy short wavelength, right, is our gamma. It's got a 0 and 0 sort of charge. In addition, sometimes unstable nuclei will emit positrons, which are like electrons with a better attitude. Thank you for the non-laugh. I appreciate that. Which oddly enough does use the exact same sort of formulas. That's right. I'm here twice a week. It's all right. But only for a limited time. I'm only here for another week and a half, and then I'm done. I'm out of here. So get your tickets now. All right. So positrons, they actually do use the sort of same symbols as beta particles. If it is the positron, they definitely will sort of indicate it somehow, even if they just simply use the beta symbol. A lot of times they'll just put like a plus or something on it, so you know that it's the positron rather than the beta. And sometimes with the beta, they'll put a negative. But if you just see a beta symbol with nothing really written, it's probably safe to assume that it's the beta particle rather than the positron. Usually they will sort of distinguish the positron rather than the beta particle. Some of them as well will, as we'll talk about, go through a reaction is sometimes referred to as an electron capture, which is basically shooting an electron at something and it captures it. So we went through those a second ago. So our atomic number again is our bottom left there, which is our number of protons in an atom. Just also a reminder that that is really the definition of atomic number, is not the electrons, right? It's just the protons. Mass number, again, protons and our neutrons. And if we subtract the two, right, we take the top number minus the bottom number there, our mass number minus the atomic number, that will give us our number of neutrons that it has in there. Can we find the mass number on the periodic table? I know you nodded, but I said no. I'm going to say no, we can't find it on there. And it's not the bottom number, right? The bottom number is the atomic mass. I appreciate that. Thank you. So the bottom number is the atomic mass, not the mass number. As you might remember, when you calculate mass number, atomic number, protons, electrons, and neutrons, they all has to be positive whole numbers, right? And obviously the bottom number there, which is the atomic mass, is definitely not whole numbers when you look at it. So here are some of our fun symbols. along the way here that we will come across in nuclear chemistry. And again, there are a couple of symbols used for a lot of things. The proton, this is one of the symbols, and obviously here our hydrogen. Our hydrogen does not have, right, a neutron, right? It has a proton and only an electron, so its mass number is 1 and 1 in that case. And then our neutron is also used a lot, so that's an N usually with a 1 and a 0 on it. And then here's our different symbols that we talked about here, really our beta particle and our alpha and our positron. So depending on the type of radioactive particles that are coming off in a radioactive decay, they will penetrate further in, say, something like lead. So as you can see there, alpha particles, not so bad, doesn't penetrate too far. If you're using something that's a beta emitter, a little bit further there. And if you're using something like gamma, you should step out of the room probably there as it's going through everything, right? If you happen to be working with radioactivity, which might happen in the science field, I suppose, you should always be aware of what type of emitter it is, and that way that you can use the proper sort of protection. Sometimes you just need like a lab coat and some gloves. Sometimes you need some lead, some concrete, and a lot of distance. Yes, depending on what you're using. So make sure that you do check that out for yourselves. Sometimes people don't mention those fun things like, hey, you're standing over an entire radioactive sampling there, you might want to step away and stuff like that. Here's some more symbols in case you missed the first 3 slides of these symbols, and they still look the same. So let's talk a little bit about balancing nuclear equations. I know we just talked about nomenclature, and now we have to talk about balancing again. And balancing nuclear equations is quite difficult. There's a lot going on that you have to keep track of. I'm joking with you. It's really just adding, so it's not too bad at all, just so you know. I was waiting for everybody to like stand up and leave. Bless you. So a couple of things about nuclear reactions, as we'll talk about, that are different than regular chemical reactions. Nuclear reactions, there really is no conservation of elements. And that's because nuclear reactions happen in the nucleus. And when we talk about protons, electrons, and neutrons, the one particle that's really important in terms of what element it is which one tells you what element it is? It is the protons, which is the atomic number, right? So since all the reactions in nuclear chemistry happen in the nucleus, is where we have our protons and our neutrons housed. We actually do change protons into other things or neutrons into other things. So because we actually do change protons a lot of times in these sort of processes, we don't actually end up with the same elements we started with. And that's very different than in a chemical reaction, right? In a chemical reaction, all we play with are electrons, right, which are outside the nucleus, right, breaking bonds, making bonds. So that's why when we have a chemical reaction, we have to balance the equation, because if we started with 4 carbons, we should end up with 4 carbons, maybe in some different things as they broke bonds and made new bonds. But in nuclear reactions, we definitely get brand new stuff formed and new elements formed, so we don't have that conservation of those elements because of the protons being changed. So when we go to balance a nuclear equation, there's really 2 things that you have to make sure of. Basically, the first thing is when you add up all of the mass numbers on the left-hand side, like we got going on here, that looks like a 236, I was gonna say 26, but 236, if we add that together, and if we add up all the mass numbers over here, that is also a 236. That is a 138 and 96. And there's a 2 in front of here, which means you got to multiply that by 2, right? Just like it kind of would distribute. And that would mean that that is balance. And the second thing that you have to do is you have to figure out and make sure that the atomic numbers on the left-hand side, which is 92 in this case, add up to the atomic numbers that are on the right-hand side of the arrow. So that is how we go about balancing a nuclear equation, is to make sure that both the mass numbers on the left and right-hand side of the arrow are equal to each other, and the atomic number on the left-hand side of the arrow and the right-hand side of the arrow are basically equal to each other. So in most cases like this, you would probably, for example, maybe be missing something. So let's just say we had just the first part of this equation here. maybe. So we had 235 uranium 92 plus a neutron. And we'll go with a $138 there and a 55 and a cesium and like a question mark. That's good. So if you had something, for example, like this, and obviously you're looking for what is missing. So what you would really want to tackle first is probably the atomic number, right? Because the atomic number is again going to tell you really what element's missing, right? So that's the one that you want to focus on, really the number of protons. So we would add up here 92 on the left, and we have basically a 55 and 0. So basically, if we just subtract those two, we take our 92 minus our 55, that's going to give us 37 as really our missing sort of element in this case. All we have to do then, right, is go to the periodic table and find number 37 that's up there, and we'll see it is RB, right? So that's usually when you're trying to balance these things and something's missing. That's where you want to start atomic number, use the periodic table. Periodic table is your friend when you're balancing these type of equations. To do the mass number, we'll do the same. On the left-hand side here, we have 236. On the right-hand side, we have basically 138 and 2, which is 140. So basically, we just subtract them from each other. And that will give us our missing sort of mass number in this case, which looks like it's 96. So that is one way that you will come across these sort of problems. Something's missing, you got to kind of find the missing thing. I would say in most cases, the missing sort of thing would probably be an element, but also remember that it could perhaps be a particle that's being given off, like a neutron, an alpha particle, a beta particle, or something like that. So you get kind of a weird number for the atomic number. It could be a particle that's missing, and that would be what is missing. Now, there's a couple of sort of terminology that's also used when we go to sort of do these type of equations. That's important when you are writing it out yourself and writing the balanced nuclear equation. So in nuclear chemistry, where they say it decays through alpha decay, that means that the alpha particle is coming off on the product side. If it emits an alpha particle or emits a beta particle, that also means that the particle is going to end up on the product side. If it's something like an electron capture, that means that the thing's hugging it on the reactant side, right? The electron. If you bombard something with like a neutron, that also is going to mean the neutron is going to be on the reactant side. So sometimes in words, if you see bombardment or something like a capture, that particle is going to be on the reactant side of the arrow. Something that's emitted or decaying through this process means that those particles are going to end up basically on the product side. Questions on that there? Hug your electron. Let's try one. So PO 212 there decays through alpha emission. Write the balanced equation. If you have a periodic table, you might want to reference it. But you're young, you have better eyesight. You can see the one on the wall. I think PO there is 84, if I can see that far. That's not bad. Not 80. Is it 85? No. Get my driver's license back. It's bad. I do the eye to cover your eye. I didn't do the eye test like that. Okay, so let's take a look at it. So here we're going to start with what was given to us. And obviously, again, the top number there is our mass number. We once again could go to the periodic table and grab our atomic number of 85 minus 1, which is 84, I think. So I think that's an 8, something like that. This is going to decay through alpha emission, which means our alpha particle will be on the product side, and you could represent the alpha particle whichever way you like. You could do that, or very commonly people will also just write sort of the helium symbol. So whichever one you want to use there is okay. So really what we're looking for now is sort of like what is missing at this point. So we want to focus in really on the atomic number here. So we have 84 on the left, we have 2 on the right, which means if we subtract it, our sort of missing atomic number is 82. We return to the periodic table and find number 82, which is our friend lead, I hope, yes. We're going to do the same thing for our mass number, which is up on top. So on the left-hand side, we have 212. On the right-hand side, we have 4. So if we subtract that, that's 208. And now we should have our balanced equation here. We got 212 for the mass number on the left and 212 on the right, and 84 and 84 in this case. Once again, no conservation, obviously, of the elements as neutrons are changing into other particles and so forth in this process. Any questions on balancing them there? Not too bad. All right, so let's take a look at I agree, that's good. A little bit more about some of the differences here between chemical and nuclear processes, as we sort of touched upon. Again, chemical reactions only involving electrons, which has nothing to do with the nucleus. And again, that's why we really do have the conservation of those elements. They just end up in different places. But pretty much the nuclear reaction is all about playing with everything in the nucleus. So we're definitely changing protons into other things and maybe adding protons and so forth. So we do find ourselves, as it goes through decay, kind of moving on the periodic table, forming new elements along the way. And they do become different elements, right? Which is one of the tenets there of Dalton's atomic theory, which was incorrect, right? That you can't kind of destroy anything and make it into something else in terms of elements. And that's really the reason here. Also isotopes, right? Which are the same element, but different mass number or a different number of neutrons, right? Means that they don't all look the same element, the atoms of them. So let's take a closer look at what's sort of happening in each of these processes here. And we'll talk a little bit about sort of what's going on here. So when we have a beta decay, in the case, here's a couple of examples of the beta decay. We get a decrease in neutrons by 1 and an increase in protons by 1. We're not going to worry about the neutrino here, which is what these guys are. So they have no mass or anything like that. So you don't have to worry about putting those in or anything like that into equations. But what's happening here ultimately when we do go through a beta decay is we're going to take a neutron from the nucleus and we're going to turn it into a proton, and it's going to give off that beta particle in the process of it sort of converting from a neutron to a proton. So overall, what happens is we get no change in the mass number, and we do change the atomic number by 1 there, as you can see. Again, because this is negative, we actually have to go up 1, right? So 7 and -1 is 6, and that matches the 6 on the other side. Now, there is no overall change in the mass number, but if you sort of did it like it doesn't really happen here, but it's like in a step-by-step process here, we are going to lose a neutron, right, in this process, which means that would take us to a mass number of 13 and 6. We then will gain a proton, in this case, which takes us back to a mass number of 14 and up to 7 in this case, which then gives us to our nitrogen. So overall, this number doesn't change from where it started, but there is a transition, obviously, of losing a neutron, but we're putting back the proton, and because the mass number is protons and neutrons, there's a net no change that occurs, but we are really transitioning a neutron into a proton in this case. Any questions on that there? Positron decay here. Again, same idea. We get kind of no change overall in the mass number. We do go up or 1 down in terms of the atomic number to balance it out. In this case, we're actually taking a proton and it's going to be converted into a neutron. So similar sort of process. If we look at the first sort of guy there, we're going to ditch ourselves here a proton, which means we will take our mass number down to 6 or to 10 and our atomic number down to 5. And obviously it will no longer be carbon, but it will now be boron. We then add ourselves a neutron in this case, which takes us back up to 11 and 5. And we end up with our boron at the end. So overall, again, no net change in the mass number, but really there is change going on. It is that proton being converted into a neutron. Again, the result of that process is going to release that positron emission or particle from the nucleus. Our electron capture, which as we were talking about there a second ago, is where we will find our particle on the reactant side. And in this case, actually the electron and the proton in the nucleus will sort of merge together here to form us a neutron in this particular case. And you could get that by just adding those two together. You're left with 1 on the mass number and 0 on the atomic number in this case. So when we do this, our argon, for example, doesn't change mass number, but we do change the atomic number in this particular case. And down here's the biggest change that you'll have is that alpha particle being emitted, and we do change our mass number by 4 and our atomic number by 2. Now, fission, for example, is a natural or spontaneous fission, as it says there, is a natural process where basically unstable nucleuses start to go through the decay process, and they will continue to go through the decay process until they pretty much hit something that's stable. And as they're going through this decay process, they oftentimes will emit particles like neutrons, and usually a lot of energy that goes through it. You can also start this process yourself by shooting a particle like a neutron at a stable nucleus, and it will go through this fission reaction where it will continue to sort of decay and give off energy. Fission reaction is like the reaction we use like for nuclear power plants, right? Is the fission reaction that occurs, gives off a lot of energy in that process. And it can be spontaneous, or you can actually cause it to happen yourself by initiating it with a particle. Here's a table similar to one you got in your book of all the particles that we just talked about and the changes that happen. All right, so let's try one more here. Potassium 40, what is the balanced nuclear equation? They don't make them as big enough anymore. I don't know. Let's make them bigger. I know. They actually did. Originally in this room, there was one on each side. Made it much more convenient, just so now. They put a whiteboard up here for, I'm not really sure why, and a corkboard. And a rolling whiteboard as well in the back. I'm not really sure. Yeah, there's a lot of drawing happening in this room. And that one in the back there, which is, I'm not really sure what you do with that one, but it looks very scary. But okay, so let's take a look at this one. This is potassium 40. By the way, again, when it's written like this, dash a number, that is the mass number, right? So that means we got a potassium, we got a 40. We could go to a periodic table that's not laminated and reflecting off the light here and see that is 19 is the atomic number in this case. This is a positron emission, which means our positron particle should be on our product side. And again, here you could use either the E or the beta symbol. Either one is used, but it is a +1, unlike the beta particle, which is a -1. So here we're just going to look to balance. We're going to start with our atomic number. So we got 19 here. We got 1 there. So that looks like an 18 is our missing. And 18 on the periodic table there is our friend argon. Looking at the top here, we got 40 on the left and 0 on the right, which means 40 over here would be a winner. And that again would be our balanced equation in this case. Any questions on that one there? All right, a few more here to finish it up. As I go through all these slides here. There you go. All right, knock these out. Let's get some balanced equations for each. Okay, so let's take a look. We'll start here with U, which is uranium. Again, all these written, the numbers that we see is the mass number. So that's going to be a uranium 238. We could go to the periodic table and grab the atomic number, which is 92. This is going to be an alpha emission, which means our alpha particle will be on our product side. And again, you can use the alpha symbol or the helium symbol if you like, but it is 4 and 2, which is the important part there. We're going to shoot for our atomic number here first. So we got 92 on the left and 2 on the right, which means our missing atomic number there should be 90, referencing our periodic table. That's a little TH. And we're going to take 238 on the left and 4 on the right and subtract them. 234, I think, in that case. Any questions on that one? Coming to the next one, that is neon, which is 24 up on top and 10 on the bottom. Once again, here we have an emission, which is a beta emission. So that's a 0 and a -1. And again, you can use the E symbol if you like. Remember that this is -1 over here, which means we actually need to go up to 11 to balance it out, right? And that's going to push us to our friend sodium. And we're going to take 24 minus 0, which will give us 24 in this case. Yeah. Questions on that one there. Positron emission of nitrogen 13. Atomic number of nitrogen is 7. Once again, emission means our particle will be on the product side. You can use the E or the beta symbol here to represent your positron. This one, though, is actually +1, which means we're going to subtract those two numbers. 7 minus 1 is 6, and that's going to give us carbon. And 13 minus 0 is 13 up on top there. And lastly here, this is an electron capture done by beryllium, which is 7. And that is number 4, I think, on the periodic table. Here, electron capture means that that's actually going to be on the reactant side here. So it's going to be joining up like so. Here, we're just going to really add the two bottom numbers in this case. So that's a 4 and a -1, which gives us a 3. 3 on the periodic table is lithium. And 7 and 0 is 7 in this case. Any questions on how to write balancing equations here? Not too bad, right? The whole final should just be these. What'd you give your Chem 51 class for the final? I just had them balance some nuclear equations. It sounds very difficult, doesn't it? Like, geez, wow, that might have took all day. All right, any questions on how to do that there? All right, we'll talk a little bit about stability here to finish out. I think we're going to talk a couple of ways we look at stability. Good talk. Let's go back. One way that we talk about stability here is N over Z. I'm going to go with neutrons over atomic numbers. That's neutrons over protons is what we're looking at here. So we got the ratio of neutrons to protons here, or N to P. And if the ratio of neutrons to protons is too high or too low is really important in terms of stability. If that ratio is too high, it needs to really kind of come back down, the neutron to proton ratio. And the way it does that is it will convert some neutrons into protons via a beta decay process. So if you check something for stability by doing the neutron to proton ratio and you find it's too high, that guy will then go through beta decay. And it may not perfectly sort of correct it, what you get at the end of that sort of first process, but it should move your ratio back towards, sort of okay. It shouldn't move you further away and go in the wrong direction. Now, you could also look at the neutron to proton ratio, and if you find that it is too low, what's going to happen in that case is protons are converted to neutrons via positron emission, or you can also do an electron capture. You could also go through alpha decay, but it's not as efficient, so we probably won't use alpha decay for this situation. We'll stick to these two. Now, you may be asking yourself, is that two different things? Why do I have an option of a positron emission or an electron capture? So we just did a electron capture here on the bottom right here for our beryllium. So if we did an electron capture or a positron emission, and if we did this same guy, but it was a positron emission in this case, we would end up with a 3 to balance it out, which is lithium, and a 7 on top. You will end up with the same product. Yeah. So that's why you have an option of 2 there. You could do an electron capture or a positron emission. They both will end you with the same basically guy at the end. So you could do either one. Questions on that there. So how do we know if our ratio is too high or too low? Well, we clearly need to look at something. And this is what is referred to as the valley of stability, the yellow there. Or if you don't like that, some books call it the belt of stability. So that's the belt/valley of stability here. And this ratio within the stability is a stable sort of situation. So when we're talking about being too high, you'll find your ratio up this way. And as it does that decay process, it should move the ratio closer to that valley of stability. Again, if you find yourself too low, it's going to kind of bring you back up to a better ratio. So how do we look at it? If you have something that has basically an atomic number of 1 through 20, the acceptable stability is a ratio of 1. As you go from 20 to 40, the acceptable neutron to proton ratio is 1.25. As you go from 40 to 80, it is 1.5. And again, anything above kind of 82-ish there is going to be not stable anyway, so you don't have to really worry about it too much. So I will say that, as you can see, this guy ends at 20 and this one starts at 20, and obviously this one ends at 40 and this one starts at 40. So there is sort of a grayish area as you roll between the two. So to keep it for us, and again, your book may not do this obviously, but just to keep it simple for us, we're going to use these as really hard cutoffs. So any type of problem that you come across in here, we'll use these cutoffs as really hard cutoffs at either it is that number or, it's too high or too low from it. So personally, we'll go 1 to 20 and then kind of like 21 to 40 and then like 41 up that way. And we'll just use them as a hard cutoff. Again, your book and stuff like that may not do that. There's sort of a grayish area as you kind of transition from one to the next. They'll go, it's kind of okay and stuff like that. So I'll try not to give you anything that's in that grayish area, but we'll just use these as really hard cutoffs. And again, either it is or it's not that number. It's going to be too high or too low. Any questions on that there? So if we look at an example here, magnesium 22. So if we look at magnesium 22, that is the mass number. And if we go to the periodic table, magnesium's atomic number is 12. So if we want the N to Z ratio here, we need the neutrons. And again, that is our mass number minus our atomic number, which gives us 10 for our neutrons in this case. And we obviously have our number of protons here, which is our atomic number, which is 12. So we're going to do a 10 divided by 12 in this situation. And that's going to give us 0.833. So obviously magnesium falls within that 1 through 20 in terms of its atomic number, which means the acceptable ratio there for it is a ratio of 1. So our N to Z of 1 here would be stable. So clearly here we are a little bit low in terms of where we want to be. So because it is low, as we saw on the previous slide there, we're going to go through one of those two options, either a positron emission or an electron capture. And if we do that there, we could actually write the equation to see what we get. So if we did our electron capture in this case, we will end up with 12 and minus 1, which is 11. I'll just do it way over here. And 22 minus 0, plus 0 there is 22. 11 on the periodic table there is sodium. So that is what we should end up with. Again, if you also did the positron emission instead, you will end up with, again, the same thing here, obviously 22 and our 11, which is our sodium. Now, when we look at what we formed in this case, if we now do our N to Z ratio on this sodium that we ended up with, our number of neutrons in this case would be 22 minus 11, which is 11, I think. And number of protons here would be our atomic number, which is 11. So now when we do our N to Z ratio, we are at 1. So we definitely increased it, right? Brought us back closer to a more stable ratio. We actually hit pretty darn stable on this. That's not always the case. So you won't always hit perfect doing it. And if you're asked any of these type of problems, you only really need to do the equation one time. You don't have to keep going until you get like a perfect ratio or anything like that. So you just do it once and figure out what you get. But whatever you do get as a result of that decay process should move you closer to the acceptable sort of ratio. Question on that there. All right, let's lay it up there.